All right. 2 o'clock. Who's out there? I have Geo, Zoe. Welcome, y'all. Welcome to elementary algebra. So let's look at our last exam here. So we want to solve for x. So if we look at number 1, here's our x. So we got to get rid of this 2 and this a and the b. I recommend getting rid of this first. All right, so we take this guy, give us some room here. So to get rid of this a, we'll subtract a. But whatever we do to one side, we have to do to the other. Now we also have this minus b. So to get rid of it, we'll add b. We have to do that to both sides. So you can see the plus a and the minus a, the minus b and the plus b cancels out. We did that on purpose. So now we're left with a 2x. And then we have all this stuff on the other side. So now we want to get rid of this 2. So we'll divide both sides by 2. Notice we had to divide this whole side here by 2. And we did that so that these 2's will go away. And look, we're just left with our x. I'll write it right over here. X equals all of this. And then we'll put the red box around our answer to make it easy to grade, right? So any questions about number 1? Okay, number 2. So we want to get our x by itself. There's a 3 and a y and the z. So let's get rid of this z first, and then we'll deal with the multiplication. So what we do, we're going to make a new equation. We'll take this guy here. Give ourselves some room. So that minus z, to get rid of it, we'll add z. We have to do it to both sides so that that and that go away. So now we're left with this 3, an x, and a y, and all of this on the other side. So now we've got to get rid of the 3 and the y. So in order to do that, we'll divide both sides by a 3 and a y. So that 3 goes away, that y goes away, and we're left with our x. So we'll rewrite it over here. X is equal to this stuff. It's not too bad, right? Now we put a box around our answer. And that's it for exam number 18. Okay. Simple steps, they work for all the problems. And that makes it quiz time. Quiz number 19, I believe. Let's solve for x. And let's see, I'm going to put 2x plus 3y equals z plus 1. And let's do an x, throw one a little different at you. X minus 1 over 2 equals 3y. All right. This number 2 here, I recommend you try to get rid of that 2 first. All right, that's the tip. Now we'll take Should be able to do these in 10 minutes. So let's get back together at 2:15. And I'll put y'all out in the breakout room out here. Breakout rooms. All right, let's work this quiz here. So we want to solve for x. Here's our x. We got to deal with this 2 and with the 3y. So I recommend we deal with this 3y first. So what we're going to do is create a new equation from this one. Make ourselves a little bit of room. So to get rid of this, we'll subtract it from both sides so that those go away. Now we have this 2x and then this stuff over here. So to get rid of the 2, we'll divide both sides by 2. Notice I divided the whole side by 2. Divide the whole thing. The 2's go away, and we're left with x. And it's equal to this stuff. And then we put a box around our answer. All right, pretty easy, right? Got rid of that, and we got rid of that. So this one's a little different. Here's our x. It's kind of hard to get rid of this first, all right? Notice x minus 1 over 2 is really x over 2 minus 1 over 2. We separated it. Okay, so what I recommend doing is getting rid of this 2 first. So what we're going to do, we'll make a new equation from this one. And what we're going to do is multiply both sides by 2. So that that and that go away. And now we're left with this x minus 1. On this side, 3 times 2 is 6. All right. So now we just have to get rid of this 1. Now we'll create a new equation out of the old one. Make ourselves some room. So to get rid of that 1, we just add 1 to both sides. So that and that go away. Now we have x all by itself. So I'll write that over here. X is equal to this stuff. And we'll put a box around it. And that's it. Any questions? All right. Y'all keeping up with the homework and Alex? All right, good.
The homework seems like I get something, so I don't do the 4, 2, or 3. But don't.
Yeah, you gotta come back to it. You work on it a little every day.
Yeah, I try that. I try coming back to it, and I'm still stuck.
Well, again, you got 2 giant tutoring labs right across the hallway. Make sure you take advantage of that. Okay. So we did 10.6 last time. So now we're going to do 13.1, then skip to 13.5. So at the end of 13.1, remind me not to keep going. Remind me to skip to 13.5, okay? So let's find our modules here. We just did a quiz and an exam. No, we're gonna have one every day, just like we have had every day for the whole semester. Yeah, make sure you get them in by midnight every night so you can get full credit, okay? Um, Come on, Alex, you can do it. Man, scam likely is hitting me up hard today. 458. Oh, what is this? Test alert. Northwest Vista fire drill. Okay. So let's find 13.1 here. Chapter 13. Let's get a snapshot. We're on page 753. So we're going to do 13.1. So mathematics to compute cost. So Trevor is a dance instructor and wants to host a one-day dance event. He has a fixed cost of $200 to rent the dance studio. In addition to host the event, he has the following variable costs, which depend on the number of participants. $1 per person for coffee and breakfast snacks, $7 per person for lunch, and $1.20 per person for a step sheet booklet. If N represents the number of participants, then Trevor's cost for the event is given by cost. $1 times the number of people, and that's for the breakfast and snacks, plus $7 times the number of people, and that's the cost for the lunch, plus $1.20 times the number of people for the step sheet booklet, plus the $200 to rent the place. This expression is called a polynomial. Terms of a polynomial are separated by addition, and sometimes a polynomial can be simplified by adding like terms. In this case, the terms adding the variable n are like terms. So the 1n could be added to the 7n, could be added to the $1.20n. So you can see that right here, what they did is they factored the n out. They only have n written once. So this would be n times this, times this, times this, like they have up here. All I did was factor out the n. And then you can add all these numbers together. So 1 plus 7 plus 1.2 gives us 9.2. So the cost is $9.20 times the number of people plus the $200 rental fee. Okay. So 13.1, page 754, it has 5 subsections. So we're gonna learn about exponents, more on exponents, multiplying and dividing, simplifying with exponents, and applications of exponents. All right, so here's our review of exponents. Remember addition, if you add something over and over again, we invented multiplication for that. So like 3 plus 3 plus 3 plus 3, that gets old. So we invented multiplication. We would just write this 4 times 3. Well, what if I have 3 times 3 times 3 times 3? What if we're repeatedly multiplying? Well, that gets old, so we invented exponents for that. This is 3 to the 4th power. That's what an exponent means, just multiplying it over and over again that many times. So b to the n, whatever b is just b multiplied by itself n times for whatever number n is. And that's what an exponent is. B is the base, so here 3 would be the base, and then 4 would be the exponent. And here we're only concerned with positive number exponents. Like in higher level math, you can have decimal exponents and all that kind of stuff. It's where you get into fractions, fractals. You have fractional exponents, right? And weird stuff. You can do all kinds of cool, weird stuff in math. But we're sticking with the most basic, simple expression. Again, the exponent just means multiply this times itself that many times. So here's a couple of rules. If I have, say, 3 to the 2nd power, and I'm multiplying this times 3 to the 1st power, well, this first one is just 3 times 3, right? And then 3 to the 4th is 3 times 3 times 3 times 3. Well, how many 3's do I have here? I have 6 of them. This is 3 to the 6th. So all this is it says you can just add the exponents. This is 2 plus 4. So if you have a like base, you can add the exponents. So let's say to write this generically, if I have a to the n times, oh, let me do b, I'll use the letter b. If I have b to the n times a b to the m, this is b to the n plus m. So if you have a like base, you just add the exponents, right? Just add those together. So this is the general form of this example. All right, so this is rule number 1 of what you can do with exponents, right? So if you're multiplying, you just add the like base. Again, you can see it in this example here. 3 squared is 3 times 3. 3 to the 4th is 3 times 3 times 3 times 3. How many 3's are multiplied together? 6, or 2 plus 4. All right, the other one here is, what if I had 3 squared to the 4th power? What if I have an exponent to an exponent? Well, this thing says multiply this times itself 4 times. So this would be 3 squared times 3 squared times 3 squared times 3 squared. That's what that exponent says, right? Take this and multiply it by itself 4 times. So that's what I did. Well, each one of these 3 squares is just 3 times 3, right? So that's this. And I have times 3 times 3 times 3 times 3 times 3 times 3. So each one of these is just a 3 times a 3. Well, how many 3's do I have multiplied together here? I have 2, 4, 6, 8. 3, 8. Notice that 8 is 2 times 4. 2 times 4. So what it's saying is, if you have an exponent to an exponent, you just multiply the exponents. So that's rule number 2. Okay. So those are your 2 basic rules for dealing with exponents here. Okay. So let's look at an example. So 6 squared is just 6 times 6, or 36. Negative 1/2 cubed, this is negative 1/2 times negative 1/2 times a negative 1/2. A negative times a negative times a negative gives us a negative. 1/2 times 1/2, 1/2. 2 times 2 is 4, times 2 is 8. So this would be a negative 1/8. 0.8 to the 4th power, that's 0.8 times 0.8 times 0.8 times 0.8. So if we plug that into our calculator, 0.8 times 0.8 times 0.8 times 0.8. This is 0.4096. You plug that into your calculator. Let's look at another example here. 8 cubed. This is 8 times 8 times 8. If we plug that into our calculator, 8 times 8 times 8, this is 512. Negative 1/4 squared, this is negative 1/4 times a negative 1/4. A minus times a minus is a positive. 1 times 1 is 1. 4 times 4 is 16. Now, let me show you something here. Negative 2 cubed is not the same as negative 2 cubed. All right. These parentheses mean take this whole thing and multiply it by itself 3 times. Okay. Actually, these do turn out to be equal, but unfortunately, I should do a different number. But so negative times a negative times a negative is negative. 2 times 2 times 2 is 8. Okay. This is a negative, and then a 2 times a 2 times a 2, which is also negative 8. All right. But typically these things are different. I picked a horrible example. They happen to be equal coincidentally. Okay. But notice this one, you have the minus sign 3 times, right? So what if I change this to the 4th power instead of cubed? Then you would have another negative 2 here. 4 minuses make a positive, and 2 times 2 times 2 times 2 is positive 16. Negative 2 to the 4th without the parentheses, we have the minus, and then there's 4 2's multiplied by one another. You see, so these in general are not equal. So be careful where the parentheses are, right? Those parentheses say, take this whole thing and multiply the whole thing. Whatever's in the parentheses is raised to the 4th power. Okay. So 0.2 to the 4th is 0.2 times 0.2 times 0.2 times 0.2, 4 times. If we plug this in, 0.2 times 0.2 times 0.2 times 0.2 is 0.0016. Note that if no exponent is explicitly written for an expression, it has an implied exponent of 1. So b is the same thing as b to the 1st power. 2 is the same thing as 2 to the 1st power. Anything to the 1st power is just that number. 3 is the same as 3 to the 1st. That's why we just don't bother writing 1 as an exponent, okay? Because it's just that number. The other thing is anything to the 0 power is 1. So 2 to the 0 power is 1. 3 to the 0 power is 1. 6 to the 0 power is 1. Anything to the 0 power is always 1. Okay. So these are a couple of other things you need to remember. So particular care must be taken when evaluating exponential expressions involving negative numbers. All right, this is what I just went over. That minus in there. All right, the -3 squared is -3 times a -3, which is 9. But the minus without the exponent, that's a -1 times a 3 squared. So you have your minus and then a 3 times 3, which is -9. Okay. Let's work some more examples. So -5 to the 4th, we have a minus sign, and then 5 times 5 times 5 times 5. 5 times 5 is 25, times 5 is 125, times 5 would be, I think, 625. Let's use our calculator and make sure. 5 times 5 times 5 times 5, 625, yeah. But this one is -5 times -5 times -5 times -5. We have 4 minuses, which make a positive. And then 5 times 5 times 5 is 625. So these happen to be equal, okay? It's because it's to an even power. The minuses all canceled out. This one, because the minus is inside the parentheses, we have to keep this minus every time. So a minus times a minus times a minus is a minus. 0.2 times 0.2 times 0.2 is what? 0.008. 2 times 0.2. Yeah, 0.008. 2 times 2 times 2 is 8. And we have a tenth and a tenth and a tenth. So each one of those decimals there moves the decimal to the left once. This one, we have a minus. Then we have 0.2 times 0.2 times a 0.2. All right, so we keep our minus, and then the 0.2 times itself 3 times is 0.008. Okay. So these happen to be the same. Oh, this one I got wrong here. Look at this. This minus sign, where did it go? I just forgot about it, right? So this one, the minus sign stayed there. This one, we had 4 minuses. 4 minuses all cancel one another out. So notice these are not equal. Okay. Down here, these happen to be equal because this one we have 3 minus signs, which is the same as 1 minus sign. Here we have 1 minus sign that lingers here. Okay. Sorry about that. Another example. -2 to the 4th. So we have a minus, and then 2 times 2 times 2. So we keep this minus. 2 times 2 is 4, times 2 is 8, times 2 is 16. This one is a -2 times -2 times a -2 times a -2. 1, 2, 3, 4 minuses, they all cancel out. And the 4 2's give us 16. So notice that these are not equal, all right? These are not the same thing. This one here is a -0.1 times a -0.1 times a -0.1, which would be minus times a minus is plus, times a minus gives us a negative. Then this would be 0.001. Okay. This one, we have a minus sign, and we have 0.1 times 0.1 times 0.1. We have our minus and then 0.001. All right, so these happen to be equal, but it's just by coincidence, right? This one, we had 3 minuses, which is the same as a single minus. This one, the single minus sign just stayed till the very end. All right, evaluate the expression for a equals 2 and b is -3. So all we do here is we replace a with 2. When they say evaluate, they mean just simplify the number. So this is 5, and then 2 times 2 is 4. 5 times 4 is 20. So 5a squared is 20. When they say evaluate, they mean plug the numbers in for a and b and find out what that number is. Now 5a squared, this is 5a times 5a times 5a times 5a, all right? It's easier to plug the number in first. They said a is 2, so let's plug the 2 in first. So whenever you have exponents, you have to do this first, all right? 5 times 2 is 10. And 10 squared is 10 times 10. So this is 100. All right, here's another rule. I'm going to go back up here to where we had the rules. Is this it? Yeah. Let's say I have a times b to the n. All right, well, let me do a generic. Let's say I have 2 times 3 to the 4th power, right? Well, that's going to be 2 times 3, 2 times 3, 2 times 3, 2 times 3. These are all multiplied together. How many 2's do I have? 1, 2, 3, 4, right? How many 3's do I have? I have 4 of them. So when you have things like this that are multiplied together to an exponent, you can just put that exponent to both of them. So if you have something times something to the power of something, this is just the first thing to that something times the second thing to that something. So it's another rule for exponents. But if you just remember what an exponent is, it means take whatever you're raising to that power and multiply it by itself that many times. All these rules come immediately just from applying the definition of an exponent. All right. So this, again, you can write it out like this. Take the thing inside of there and multiply it out 4 times. Well, again, you have 4 2's and you have 4 3's. So this one is 5ab squared. So they said that a is 2, and they said that b is -3. So 5 times 2 is 10. And then this -3 squared is -3 times a -3. A minus times a minus is positive. 10 times 3 is 30. Times 3 is 90. A plus b squared. Well, they said that b is -3 and a is 2. -3 plus 2 would be a -1. And the -1 squared means -1 times -1, which is +1. Okay. You okay over there, Chloe? All right. Let's see. Okay, we did that. You know, Chloe, if I went to class and sat there with headphones on looking at my phone, I probably wouldn't learn anything. That's okay. I'm just trying to help you out there. All right, 6x squared. They say x is 2 and y is -5. So evaluating, We just plug those numbers in for those letters. So 6, we have our 6, x squared. They said x is 2, so we replace x with 2. So 2 squared is 2 times 2. So 6 times 2 is 12, times 2 is 24. This one, again, they said x is 2, so let's replace the x with a 2. 6 times 2 is 12. 12 squared is 12 times 12, which is 144. Here we have our 2. They said x is 2, so let's replace the x with a 2. And then they said y is minus 5, so we'll substitute that in. 2 times 2 is 4. Minus 5 squared is minus 5 times a minus 5. So a minus times a minus is a positive. 4 times 5 is 20. 20 times 5 is 100. So y minus x squared, they told us y is minus 5. Then we have this minus sign. And then they said x is 2. And we have it squared. So minus 5 minus 2 is negative 7 squared. That'll be a minus 7 times a minus 7. A minus times a minus is a positive. 7 times 7 is 49. So let's look at this, how to avoid mistakes here. So in the expression 5ab squared, the exponent 2 applies only to the variable b. The constant 5 and the variable a both have an implied exponent of 1. All right. So you're only squaring the b there. Oh, they had one like this, a plus b squared. This is not a squared plus b squared. No. Okay, this is important. What would a plus b squared be? This thing says take this and multiply it by itself twice. This would be an a plus b times a plus b. This says take the a and multiply it by a plus b. Then you have a plus. Now take the b and multiply it by a plus b. So you're getting an a times an a is an a squared. Then you get the plus. And then you got the a times b. Then you got that plus. Then you get b times a. Then you get this plus. And the b times b, which is b squared. So we have an a squared. These are the same thing. ab is the same as ba. So you get 2ab and b squared. So a plus b squared, you get the a squared and the b squared, but there's also this cross term here. Okay. All right. This has to do with how waves work. All right. If you have two waves, when they collide with one another, you get interference between the two waves. Okay. So cross terms is what these are called. Okay. This is the mistake that most people make the most right there. All right. Again, a times b squared, this is a squared b squared, right? But a plus b squared is not a squared plus b squared. It is a squared plus 2ab plus b squared. Okay. All right, multiplying and dividing expressions with common bases. So in this section, we investigate the effect of multiplying or dividing two quantities with the same base. So let's consider the expressions x to the fifth times x squared and x to the fifth divided by x squared. So x to the fifth times x squared, x to the fifth is x multiplied by itself 5 times. X squared is just x multiplied by itself twice. So we have 7 x's, or x to the 7th, which we could see that's 2, I should write 5 plus 2. So you just add the exponents. That was one of the first rules I gave you. This one, you have 5 x's on top, 2 on the bottom, and so you can cancel out 2 of these and you end up with x to the third. Well, what that is 5 minus 2. Okay. So if you're dividing, that's like having a negative exponent. So they're focusing only on positive exponents. Well, a negative exponent just means divide. So if we have b, well, let me do it generic, 2 to the negative 3, that minus sign tells you how many times you're dividing. Okay, so a positive exponent is how many times you're multiplying something by itself. The opposite of a positive exponent is a negative exponent. The opposite of multiplying is dividing. So minus the negative exponent, it just means divide. Okay, so what this means generically is if we have b to the negative n, this just means divide by b n times. Okay, so this will be over 2 times 2. The minus there just means divide that many times. A positive exponent, multiply that many times. Negative exponent, divide that many times. So this is another rule of exponents here. So assume that b is a number and that m and m are positive integers. So this is one of the rules, the first rule I gave you, the second rule I gave you. If you have b to the m times b to the n, this is b to the m plus n. All right, that's what we just looked at right here. Something to something times the same thing to the something, you just add the exponents. Okay. If you're dividing, here's how one way to write this: b to the n over b to the n. I told you that dividing is the same thing as having a negative exponent. Well, by this rule right here, if you have a like base, you just add the exponents. So that's what they're saying right there. Okay. So let's do some simplifying here. Page 757. All right, since these are like bases, we just add the exponents. All right, and why is that? It's because w cubed is w times w times w, and w to the fourth is w times w times w times w. So you have 7 w's. So even if you don't remember this rule, but all you know is what an exponent is, all you remember is that exponent means multiply that thing by itself that many times, you still get the right answer. So all these rules that are popping up, they're direct consequences simply knowing the definition of an exponent. So here we have 2 cubed times 2 to the fourth. How many 2's do I have? 7 2's. Or I could have been like, I can just add these exponents. It's a lot quicker, right? So another example. So q to the fourth is q times q times q times q. And q to the eighth is q times itself 8 times. So how many q's do we have? We have 4 here and 8 there. We have 12 total q's multiplied by one another. 8 to the fourth times 8 to the eighth. So we need 8 more 8s. How many 8s do we have total? We have 4 here. And then we have 8 there, all right? So we have 4 plus 8, or 12. We can just add the exponents because we have a like base. Let's look and see about avoiding mistakes here. When we multiply expressions with like bases, we add the exponents. The base does not change. All right, so 2 to the third times 2 to the fourth is 2 to the seventh. The base isn't changing. So here we have what, I'm going to write this bigger because it's hard to read. R to the sixth over R to the fourth. So this is R times R times R times R times R times R over R times R times R times R. So you can see that we can cancel out 4 of those and we have R squared. The other way to write that is R to the 6 minus 4, right? 6 minus 4. Here we have 5 to the 6th over 5 to the 4th. We can simply write that like this. This would be 5 squared, or 25. There's 6 5s over 4 5s. All right, if we have 15 y's, and then we're dividing by 8 y's, we're left with 7 y's. If we have 15 3's, and then we're dividing by 8 3's, we're left with 7 3's. And we can multiply that out if we wanted to. I'm just going to leave it like that. Page 758. So here we have, I'll write it bigger here. We have z to the fourth times a z to the fifth and a z cubed. So if you don't remember any of the rules and you just remember what an exponent is, z to the fourth is z times z times z times z. Z to the fifth is z times z times z times z times z. And then we're dividing by z cubed, which is z times z times z. So we can look at this and do this. And we're left with how many z's? 1, 2, 3, 4, 5, 6. All right. Or we can use our rules. Right here we have like bases, so we can just add. But then we're dividing by that, so we can subtract the 3. So 4 plus 5 is 9, minus 3 is 6. It's a lot quicker than writing z 900 times, right? We have 9 z's on top, 3 on the bottom. So obviously there's 6 left, right? You should be able to just look at that and write this down. Again, 9 z's multiplied together on top, 3 on the bottom, you're left with 6. So here we have 10 to the 7th, and then we're dividing by, what's on the bottom here? 10 squared times 10. Well, that's 10 cubed. Well, if you have 7 tens on top and then you're dividing by 3, you're left with 4 tens. All right, we have, just looking at this, we have 8 A's and 3 A's on top. That's what, 11 A's on top? And then we're taking away 7 of those. So 11 minus 7 is 4. You should be able to just look at this and say, oh, that's a to the 4th, because I have 11 on top and then I'm dividing out 7 of them. But using our rules, we have 3 plus the 8 minus the 7. Here we have 9 5s on top, and then we have 7 on the bottom. So 9 minus 7 is 2. This is a, not a squared, 5 squared. Why is that? Well, we have 9, and then we're dividing by 2 and 5. Dividing is subtracting the exponent. All right. So if it's on the bottom, it's negative exponent. If it's on the top, it's a positive exponent. All right, use the commutative and associative properties of real numbers to simplify. So we're just multiplying this all together. We have a minus sign here. 3 times 2 is 6. Remember when you're multiplying stuff, right? 3 times 2 is the same thing as 2 times 3. A times B times C is the same thing as a B times an A times a C, or a C times a B times a A. If you're multiplying, you can multiply these things in any order you want, right? 2 times 3 times 6 is the same thing as a 6 times 2 times 3. So these are all just being multiplied together. So we can collect these. 3 and the 2 is a 6. If we have P squared times a P, that gives us 3 P's total. We have 4 Q's times 5 Q's. That gives us 9 Q's. Here we have 16 divided by 4 is 4. We have 9 W's on top, 8 on the bottom. That leaves us with 1 W left over. We have 3 Z's on top, 1 on the bottom. That leaves us with 2 left over, right? All right, let's simplify this. It's all being multiplied. We have a minus sign here. A 4 times a 3 is a 12. We have 2 x's times 5 x's, which gives us 7 x's. We have 3 y's times 7 y's, which would give us 10 y's all multiplied together. Here we have an 81 divided by 9, which is 9. We have 4 x's multiplied by one another, and we're dividing out 1 x. So if you take 4 minus 1, we're left with 3 x's. If you have 7 y's multiplied together and you divide out 3 of those y's, we're left with 4 y's. So let's look at avoiding mistakes here. Simplify the expression, we multiply the coefficients. The coefficients were the numbers out front, right? We multiplied the 3 and the 4. But if you're multiplying with like bases, you add the exponents. All right. So let me throw in an exam here. We'll come back to this. This is for those of y'all who have to leave early. Number 19. Simplify. So number 1 here, I'm going to do a to the 5th times b to the 6th times c to the 7th. No, I'm going to do b squared divided by a to the 2nd times a to the 3rd times b. Number 2, let's do a to the 3rd times a to the 2nd times b to the 3rd divided by a times b squared. All right, so that's your exam for next time. And we could take a short break. All right. Break. We will resume. Let's see. 3:20. Okay. So we'll come back to this exam. Where were we? Applications of exponents. So exponents show up a lot when we're dealing with interest and how interest accrues. So simple interest. All right, let's see. Simple interest. We have several letters here. We have P is the principal. So how much you borrow, all right? I would be the interest that's accrued on the loan. R is the annual interest rate. So if it's like 10%, that means 10% per year. All right. So the annual is important. All right. It's implied that it's per year. So simple interest is going to give, and T is the time in years. So simple interest is I par T. I party. You can remember that, right? That's your simple interest. And again, that's where it's just the number of years. So if it's 10% per year after 10 years, well, you've doubled how much you owe, right? Because every year it's collected 10% more. That's typically not how loans work. Usually, like if you had 2 years, after the first year, let's say you had $100 you owed. After the first year at 10%, you'd owe 110, right? Well, that second year, you're going to pay interest on the interest. So it's not going to be $120 you owe after the second year. It's going to be like 122 because you also have the interest on the $10. So it'd be 121 actually. Okay. So most day-to-day applications, interest computed on money invested or borrowed is compound interest. All right. So it's interest on the principal and the interest already accrued. So that's your compound interest. All right. So using this formula, I party, if you just want to find the interest on $1,000 loan at 8% for 3 years, you replace P with 1,000, you replace R with 0.08. 8% is 0.08. And then 3 years, you replace T with 3. So After 3 years, simple interest, the interest you owe is $240. So the amount you owe, A, would be your 1,000 plus the 240, which is what they have here. A is your amount. So to deal with this collecting interest on interest, here's the more realistic formula. Compound interest. Insert. So compound interest. All right. Oh, and I should have told you up here, simple interest. So A is the amount owed after T years. So the amount is your principal plus your interest. But the interest was PRT. So notice you can factor a P out of here. Both of these are multiplied by P. P times 1 is P, and then P times RT is PRT. So this is your amount for simple interest. Now, if you're collecting interest on interest, notice it's a little different here. The amount is P times 1 plus R to the T power. Notice this looks kind of like this, P times 1 plus RT. So simple, it's R times the T. But here you have R to the T power, but it's also 1 plus R to the T power, all right? So this is your compound interest. This is the amount you'd owe after T years pass. All right, so if we're going to do an example, $1,000, 8%, 3 years, right? Same numbers as before, but this time we're going to collect interest on the interest on the interest on the interest. Because the second year you collect the interest on the interest from the first year. Well, the third year you're collecting the interest from the first year, the interest from the second year, and the interest on the interest from the first year. That's why you have this exponent, okay? But if you just plug in your numbers, you see it's $1,259. Last time with simple interest, it was just $1,240. So you can see that there's an extra $19.71, and that's from the interest on the interest, okay? Let's put a box around this. So we're not going to derive these formulas or anything. We just want to make sure that you can use them. Let's take a screenshot here. I hope I remembered to resume my recording. Yeah, good. All right, so we have 8 years. So our T here is 8. Be careful, what if they give you months? You need to convert that to years for it to work in the formula, okay? So our principal is $7,000. Our interest rate, 2.25. Well, as a decimal, this would be 0.0225, okay? Got to convert the rate to a decimal. And they say compounded annually. What that means is it's just compounded once a year. The other thing we'll just look at next is what if instead of at the end of the year, the interest is applied? What if they say, let's take 1/12 of the interest rate and each month charge you 1/12 of the year's worth of interest? That would be compounded monthly, okay? So you'll see that. So here, this is simple. It's compounded once a year at the end of the year. But later we'll see that banks like to compound more often than that. They'll be like, yeah, I'm going to do 12% yearly. What I'm really going to do is do 1% every month. Well, guess what? If they do that, you pay even more. Because that second month, you're paying interest on the interest from the first month. So the more they compound it, the more interest you're paying. And it turns out that what if they compounded it every millisecond? So after the 10th millisecond, you're paying interest on the interest on the interest on the interest on the interest 12 times over from the first millisecond. Well, each one of those is a little bit of money and it keeps adding up. But the best you can do is compound continuously. And it turns out it doesn't add up to infinity. There is a limit. And we'll get to that formula here soon. And it's an exponential. But for here, we're just compounding annually. So I'm going to say, for future purposes, n equals 1, the number of times they compound in a year. Just once a year at the end of the year. So our compound interest formula works. A equals P times 1 plus R to the T power. So we have 7,000. 1 plus 0.0225 to the 8th power. So 1 plus 0.0225 is 1.0225. So if we plug this into our calculator, I'm going to start here. And then once I get that, I'm going to multiply by 7,000. I'm going to press 1.0225. And then I'm going to hit the to the power of the hell. Oh, there we go. To the power of 8. All right. And when I do that, my calculator says 1.1948. Okay. By the way, the exponent button on your calculator looks like this. No, it's the other way around. X to the Y. That's the button you press. So you type this in, press this button, and then hit the 8. All right. So now I'm going to take that and multiply it by 7,000 times 7,000. And I get $8,363.82. Okay. So we start off with 7,000. We had $1,363.82 in interest. Okay. And these are real numbers. 2.25% interest is a pretty good interest rate, right? Your credit cards are more like 25%, you know? That means in 4 years, you've already doubled what you owe, you know? My car payment is $375 a month. Over $100 of that every month is just to cover the interest alone. And that's at 6% interest rate. Okay. Now, if you're rich, then you don't have to pay any interest at all. So the interest really is what we would call a regressive tax. It hurts the poor. They charge the poor more than rich people. You'd think like if you had less money, they should charge you less interest. The rich people should pay more interest because they can afford it. But the rich people are more likely to be able to pay it off. So they don't have to pay any interest. So it pays to have good credit, okay? Of course, the rich people just pay cash anyways, right? All right, so let's look at another example here. Of course, when you go to buy anything, I'm always getting letters in the mail. You pre-qualified for 0% interest, blah, 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 blah. And then you get there and they're like, oh no, it's 8% for you. It's like, well, why'd you tell me I pre-qualified for 0%? Well, at the bottom of the thing, there's a little asterisk that says, you know, for only people with best credit in the world. So my credit is like a 700. It's actually a 699. I have to have a 700 to get the 0% interest. Find the amount in the account after 3 years. So T is 3. The initial investment is 4,000. And our 5% interest means R is 0.05, compounded annually. So they're compounding once a year. So the amount we're going to owe P times 1 plus R to the T power. We have 4,000 times 1 plus 0.05 to the third power. So let's deal with this stuff inside of here. 1 plus 0.05 is 1.05 to the third power. So we have our 4,000. Let's take this 1.05. I'll type it in 1.05. And then I hit the X to the Y button to the power of 3. And that is 1.157625. So now I take those two numbers and multiply them together. And I get $4,630.50. So 5% interest is $4,000, 3 years. We are paying an extra $630 in interest. So let's investigate our calculator. All calculators are different, you know? So let's look at what they're saying here. So if you have a scientific calculator, right, and you're evaluating this to the 8th power, type in the number to the power of 8 and hit equals. Okay. So practice these with your calculator, because this is where most people make the mistakes. They'll plug the numbers in perfectly into the formula, but then they just type it in wrong in their calculator every time. So here you would type in 1.06, and then you hit the X to the Y button, and then you press a 5, and then you press equals. So this one here, we would type in 1.02. We hit the X to the Y button, type in 40, and then hit equals. This one, start with this. It's a lot easier. Type in 1.06, hit the X to the Y button, then hit the 5, then hit equals. And what you're going to have on your screen is this. Then hit the times button and hit 5,000 and then hit equals. So for these, it's easier. You're basically working your way from the inside out. You hit this to the power of 5 and then multiply by 5,000. Okay. All right, that's it for this section. Now we have to skip somewhere. Let's see. So we're skipping to 13.5. Let's take a look at this one. 13. There it is, 13.5. Addition and subtraction of polynomials. So this is what we're going to be doing next. Let me see. So these are pretty easy compared to a lot of this stuff. So one commonly used algebraic expression is called a polynomial. A polynomial in one variable x is defined as a single term or a sum of terms of the form ax to the nth power, where a is a real number and the exponent n is a non-negative integer. For each term, a is called the coefficient and n is called the degree of freedom. So here's some examples of polynomials. 3x squared plus 2x plus 1. 4x to the 5th plus 2x cubed plus 9. Or just x squared. Or just x. That's the simplest one. Or you could have x squared, or you could have x plus 1. Or you could have x squared plus 2. Or you could have x cubed plus 2x squared plus 3. Notice there's no x here. You only have x cubed and x squared. So the generic form of a polynomial for any polynomial, all polynomials look like this. A1, no, I call it C. I'll call it C for coefficient. These numbers are coefficients. X is your variable. So I'll say Cn x to the n, Cn minus 1, x to the n minus 1, plus C x, C sub 0, x to the 0. All polynomials look like that. Another way to write it is ax to the n plus bx n minus 1 plus all the way down to nothing. Let's see, how do they write it? Ax to the n. So each term is a number times x to a power. That's it. You have a number times x to a power and you're adding them all up. Because these are different powers, we can't combine these. So they kind of have to stay separate, okay? So these Cn, these are just names for the coefficients. It's names for the numbers before the letters, okay? So here, negative 12 z to the 7th, the coefficient is negative 12. Since it's z to the 7th, they say this is a 7th degree polynomial. So whatever the highest power of x is, that's the degree of the polynomial. So x cubed is the same as 1x cubed. So our coefficient is 1 and your degree is 3. 10w is the same as 10w to the first power. So your coefficient is 10, your degree is 1. 7, the coefficient is 7. There are no x's, right? There is, it's x to the 0 power. Remember, anything to the 0 power is 1. So if you just see a number, that's a 0 degree polynomial. You have 0 x's there. All right, if there's only one term, they call it a monomial. So if all you have is an x to the 4th or a 2x cubed, and there's nothing else added, that's a monomial. Remember, mono means 1. If there's two terms, like x squared plus 1 or 2x cubed plus x squared, if there's two terms, they call that a binomial. If there's three terms, it's called a trinomial. The term with the highest power is called the leading term, and it's the number in front of it would be the leading coefficient. The degree of the whole polynomial is the highest exponent. And you typically write them from highest power to lowest power. So they write them in descending order. Okay. So that's just a bunch of vocabulary. All right, let's look at some examples here. So these are monomials because there's only one term. These are binomials because there's two terms. These are trinomials because there are three terms. All right, the leading coefficient, there's only one coefficient. Those numbers, right? So that's why that's the leading coefficient. Down here, the leading coefficient for this guy, right? They don't write it like this. They write it like this. You put this one first because it has the highest power, and then that one second. So this is the way you would want to write it. And the leading coefficient is the number before the highest power. And the degree is 6. It's the highest power. Okay, so that's all you really need to know. So let's identify some parts here. I can't say I've ever had to use any of these vocabulary words except for the degree, just the highest power. That's what's most important. So this thing here, we would want to write this. Our highest power here is the a cubed. We would want to write it like that. And then our a cubed next. And then our 3a, and then our 6. We'd want to write it like that. Highest power to lowest power. All right. So the degree here, the degree is 4. It's the highest power. So the coefficient for that term is -2. The coefficient for this term is a -1. This one is a -3, and this one is 6. All right, so here's each of the terms. All right, this is it in descending order. The degree is 4. It's the highest power. The leading coefficient is a -2. Now evaluate the polynomial for -2. All we're doing is we're going to take this and replace a with a -2. So we have a -2 times a -2 to the 4th minus -2 cubed minus 3 times a -2 plus 6. So all we did is take this, and everywhere there's an a, we replaced it with -2. So let's look at this term by term. I have a -2 here, -2 to the 4th power. That's -2 times -2 times -2 times -2. So you have 4 minuses, so they cancel out. 2 to the 4th power is 2 times 2 times 2 times 2, which is 16. Now this one, I keep my minus sign. -2 cubed. 3 minuses gives me a minus. 2 cubed, 2 times 2 times 2 is 8. Now this term, -3 times a -2 is a +6. And then I have a +6. So if we keep simplifying, -2 times 16 is -32. A -8 is a +8. A 6 plus a 6 is 12. So here we have 20 minus 32 gives us -12. So all we did was take that expression, replace a with a -2, and simplify. All right, we'll have lots and lots and lots and lots of examples doing that. So the important thing here is to be able to write it in the order that's best, right? Again, this is equality, so they're equal. The highest power is x to the 4th. The next highest is the cubed. And then we have the x squared, and we have an x, and then there is no number without an x. So that's just writing it in descending order. The degree of the polynomial is 4, the highest power. The leading coefficient would be 8, the leading term, the coefficient of the leading term. To evaluate this for -1, all right, we have 8 times a -1 to the 4th plus 5 times a -1 cubed plus a 3 times a -1 squared minus a -1. So be careful with these minuses, right? We're subtracting a -1. So if we simplify this, -1 times itself 4 times is +1. So we're just left with the 8. -1 cubed, 3 minuses leave us with a minus. So we end up with a -5. -1 squared is +1. So we're left with the 3. And a minus and -1 is +1. So if we add these all up, 8 minus 5 is 3, plus 3 is 6, plus 1 is 7. Dang it. All right, polynomials may have more than one variable. All right. So in such a case, the degree of a term is the sum of the exponents. So this one, since this one has x's and y's and z's, all right, it's hard to say which one is the leading one, right? This one has a y to the fifth, but this one has a z to the eighth. So what order do you put it in? Usually you start with your x's and then your y's and your z's, but here this is random. Here they say the degree is you add up the exponents. So you have a 2, a 5, and a 1 gives you a degree 8. Here you have a 3 and a 1, right? I'll put the ones in. All right, you just add up all the exponents, and that's the degree for that term. Okay. All right, let's see. All right, terms are like if they have the same variables and they're raised to the same powers. So these are like terms. I could add those together. That would give me negative 4x squared. These are like terms because it's the same variables, same exponents. These are unlike terms. Yeah, we have the same variable, but they're different exponents. I could not add those together. Here we have the same exponent, but different variables. I could not add those together. Just like I can't add these together. Okay. All right, so for example, these are all like terms. I can just add them together. I have 3 plus 9 minus 2. I have 10x squareds here. Okay. So the exponents don't change. I got x cubes here, right? So 2x cubes and 3x cubes gives me 5x cubed. There's, all right, we're adding cubes here. You wouldn't end up with an x to the sixth. You only end up with an x to the sixth if I have an x cubed times an x cubed. This would be an x 3 plus 3. Remember, if you have a like base, you add the exponents. Remember, this is x times x times x, and this is x times x times x. You have 6 x's multiplied by one another. All right, so if we're going to add these. We have x squared y's, right? Just think of that as a number, right? I'll call it blob. I have 3 blobs plus 5 blobs. That gives me 8 blobs, right? It just turns out that the blobs are x squared y. All right, so I have 3 plus 5 x squared y's, or 8 x squared y. These are like terms, same variables, same exponents, so we can add them together. Here we have a squared b cubed, a squared b cubed. These are like terms, so we can just add them. 13 plus 2. These are both times the a squared b cubed. We have 15 of these blobs. All right. All right, let's call it a day. Here's your exam. And yeah, we'll call it an early day. And I will see y'all Tuesday. Bye, y'all. Bye, Chloe.